at George Washington, and he's doing some really cool stuff working with multiplex networks. This is one of the many papers he has on multiplex. He's on the job market. And, so this is one of the papers that was originally submitted to the competition, but we decided that some papers were, the content was so profound that it should not be covered in 20 minutes. So we decided to let these people talk for an hour in the regular series. With that, the floor is yours, Hector. Usually we'll take questions along the way, so it's up to you, however you want to do it.
No, whenever you like, please interrupt me. I actually prefer this than stopping and asking if there are any questions along the way. Thank you so much for the introduction, and indeed, thank you so much to the organizers for inviting me to give this talk. It's quite an honor, I have to say, as I've been following GamesNet quite closely, live and particularly in YouTube. Which I think it's an excellent idea to post the seminars there. So yes, it's a tremendous honor, and with that, I will get into it. So as the title of this paper and sort of the introductory graphic here suggests, what I do in this paper is to sort of try and understand how is it that like multiple types of interactions over a collection of economic agents, where we have different patterns of local interactions over each type of interaction, essentially. So transmit shocks, right, over the entire system. In other words, what I want to do is to sort of think about a system where we have a collection of agents that are participating in multiple interrelated, and I will come to what interrelated means later on, networks, and how sort of shocks, idiosyncratic shocks, can transmit within the system. Now, in doing so, I also want to try and say something with regard to who is sort of the agent in this system that has the largest sort of transmission capacity. Like what's the largest capacity to sort of transmit an idiosyncratic shock within the system, as well as also try and classify, like, to what extent are these types of systems prone to sort of large fluctuations with regard to aggregate outcomes. Now, I know I've said a couple of things here, so let me try and offer a bit of background in the sort of single network case. How is it that sort of these questions arise in the first place? As well as what are sort of the typical answers given within a single network. And the way I want to think about network system here is general. And indeed, if we sort of look at a variety of network models that have been written down in economics, and sort of regardless of the micro foundation that one imposes, we can generally think of these models as being comprised of three fundamental elements. And essentially, what are these elements? You have a collection of agents that are performing some action in that system, right? Or are classified by a particular state. And where does the network comes in? Essentially, we say that there is some network dependence between these states across these agents, right? So what is an example here? We can think of, say, I don't know, a financial system, right? We have a collection of banks whose state is a solvency state. They're either, solvent or insolvent. And the network is, for example, debt contracts between them, right? Or we can think of like a game structure, right? Think of the linear quadratic standard game that has been extensively studied in the literature. What you have there is, again, a collection of, you have some players playing a game, they're performing some activity X, and you have some network dependence between it, right? Now, even though most papers in the literature do not really sort of think of aggregate outcomes here, all these models sort of implicitly define an aggregate state of the economy as well, right? So in the linear quadratic game, you can have aggregate welfare. or in the financial setting, you can have sort of aggregate solvency or insolvency, right? Or say a mapping from solvency and insolvency to systemic risk, for example. And in this type of framework here, right? What we can do is to introduce, say, a distribution of shocks, right? So I can now come in and say that there is some distribution of disturbances that can occur to these states, right? And from there, two natural questions can arise, right? So the first thing that we can ask is, all right, given this distribution and given that a particular shock is realized to a particular state, like what agent is it that can cause the largest impact on this aggregator of states, right? So if you have the banking system, for example, you say, all right, which bank needs to go insolvent, not repay its loans to the majority of other banks, and sort of cause a large sort of default cascade in the scenario, right? And typically, the network answer to this question is a centrality related answer, right? Now, obviously, the micro foundation here will dictate what centrality metric will be chosen. For example, Katz-Bonacik, and I will be dealing with Katz-Bonacik in this particular paper. But you typically say, look, the most important agent with regard to shock propagation is the most central, right? Now, the second question that we can ask is that, all right, fine, I can identify key agents, but given this sort of distribution of shocks, right, given this distribution of idiosyncratic shocks, and if sort of aggregate outcomes and aggregate disturbances map to centrality, right? So if centrality is what dictates aggregate responses, essentially the network and the sort of distribution of centrality, right, induces a distribution of aggregate outcomes that I can get, right? So given the network and the distribution of shocks, then I have a distribution of aggregate outcomes that are essentially parameterized by the distributions of centralities. And intuitively, what can we think is that if the network here is sort of asymmetrically connected, we have a lot of asymmetry in centrality in the network, then the more asymmetric the responses I will get with regard to aggregate response, with regard to aggregate outcomes, right? And this is sort of sometimes referred to as aggregate volatility in the system, where essentially you're saying that, look, the more asymmetric the connectivity structure is, the more sort of, the higher the tendency of the system will be to fluctuate, right? The question also naturally relates to like tail events in the distribution. Are there any questions up until this point? Because now I'm going to get into the multidimensional stuff.
So far, I haven't seen what's the role of multiplex.
Right, I'm introducing multiplex now. I just want to set the foundation for the story so that we all are on the same page.
Okay, looking forward.
Thank you. And essentially, what this paper is about is to raise the dimensionality to this problem, right? So now what I want to do is to say, I want to come in and say, okay, this is all well and good and understood, but how exactly should I answer these questions if my agents that now populate the system are allowed to interact across multiple dimensions, right? So in a financial system, right, this is intuitive, right? Banks are not really constrained and interact with one another just by issuing short-term debt between one another, right? So this is typically the market that's investigated in the financial literature. You can say that, you know, banks are exposed through debt, they are exposed through the holdings of common assets, they are exposed to each other through derivatives contracts, etc., right? In a social system, for example, right, we can think of social media, right? It is not just the network of connections that you have in Facebook that might dictate aggregate outcomes in the social sense, but it's also your followers on Twitter, on Instagram, and all these other platforms that are available, right? And typically users are active in not just one. And essentially what sort of the topology that I'm going to use here, the interaction structure I'm going to use to raise the dimensionality to the two aforementioned problems is a multiplex network, right? And a multiplex network is exactly that. As the picture suggests, you have these manifold layers of networks here, of agents that participate in all of them, essentially. For the proper definition of a multiplex network also consists of this point here as well, that all agents have a unique correspondence across networks. Now, this is a bit vague. I will be more specific about this later. But this essentially has to do on how you couple these networks together, right? All right, we are participating in all these layers, but how are these layers sort of talking to one another, right? What's the coupling between them? And I'll be specific about how I'm going to do this in the following slide. So coming back to these two questions, well, all right, we can again now ask, given the structure, what agent here is systemically most important, or what agent here has the capacity to transmit mostly the shock across the network, right? And we look at this and we say, all right, I might have some connectivity structure in the first layer where, say, agent 1 is classified as being the key or systemically most important, whereas in layer 2 it's agent 3, and in layer 2 is agent 4, right? So who is key for the system, right? If I have to classify one of them, which one will I? Obviously, one can say, yeah, just sum over centralities or sum over the metrics, and then, whatever the aggregate centrality in that sense is, and this is key. But again, this could be hypothetically mapped to a single layer network, right? Where you sort of sum over the links. So again, this comes back to this unique correspondence here that I'm going to talk about in a bit. And the second thing with regard to sort of the distributional point I made and fluctuation capacity, there are sort of many things going on here, right? Where if you take a distribution of shocks that are of idiosyncratic nature, right? And then we know that in the single layer case, I care about centrality asymmetry. Well, in this situation, the first thing that happens when you expand the dimensionality is that, all right, you have some you have some distribution of centrality in the first layer, and then the second layer, and the third layer. So how do I sort of aggregate these asymmetries across layers, right? The other thing to note with regard to raising the dimensionality to this question is that, in a way, when you're saying that shocks are idiosyncratic in nature, but when shocks are idiosyncratic in nature, right? When you raise the dimensionality to this problem, you're essentially diversifying it in a way, right? You're saying that now there are more shocks that can be realized. Therefore, one can say that the relative effect that each of them can have on an aggregate state is less, right? But on the other hand, what I can do when I raise the dimensionality is to sort of raise the asymmetry in each of them, right? I can say that, the first layer is asymmetric, and then the second layer is asymmetric, and the third layer is asymmetric. So there is this volatility trade-off in a way, right? So we will see that this will come into play eventually. So as I said, the main sort of issue that one is faced to sort of answer these questions in the first place, and to even pose these questions in the first place, is how exactly it is that I couple these layers, right? And the way I'm going to do this is by writing down a very simple model that's going to be based on a modularity argument, a strategic modularity argument. And I'm going to go into how the model works in a bit, but essentially I'm going to say pretty much the story is that you will have a collection of agents that are populated in many layers. They are exerting a particular action in each layer, and then these actions are either strategic substitutes or complements between them, right? So this is what we're going to do. So I want to write this model down, and the thing that I'm going to say now is that the model will be sort of reduced form nature, right? I'm not going to have a particular micro foundation with regard to payoff optimization, etc. Right? So I'm going to start the model from the best response here. This is motivated by the literature, the small literature on economic multiplexes that are available at the moment. But I think there is a lot of insight to be gained, even if there is no sort of proper micro foundation. Before I get into the main model, a brief preview of the results. And essentially, and this is a bit intuitive here. Right? The results are also a bit intuitive. When you have this increased dimensionality to connectivity, right? Well, okay, if I have this type of setup, you know, and I come in and I distress some agent in a particular network, right? What is the tendency of the shock to propagate? Well, okay, the shock will propagate within the layer, within the network where the shock is realized. But now it also has the capacity to cascade across layers, right? So within network propagation, I'm going to call the intra-network margin. So this is going to be aggregate state responses due to cascades within a particular network. But now multiplex connectivity gives you an additional margin by which a shock can affect aggregate outcomes, right? And this will be a function of the capacity of the shock to cascade across. And the whole point of this paper is that I'm going to use this now additional margin to study systemic importance and fluctuation tendency, right? And indeed, one can show is that sort of the standard, and what we will show is that the standard pure centrality argument with regard to systemic importance sort of fails here. I can indeed have, say, 2 layers, right, in which in both layers, a particular agent, say agent 1, would have been classified as being most important in each layer, right, individually. But if I couple these layers through a substitutability argument, it could be that some other agent turns out to be systemically more important. And with regard to aggregate volatility, with regard to fluctuation tendency, essentially I'm going to try and do a comparison between fluctuation tendencies in the single versus the multiplex case. And under particular configurations of the multiplex and the sort of the coupling that we do between the layers, we will show that indeed this system can be more volatile than a single network system. And before I jump into the model, a brief remarks on the literature. Well, you know, multiplex networks have been studied in a variety of places, but not so much in economics. I highly recommend this paper here. It's a survey of multiplex outside economics, very compact, and it's sort of very formal, very formalized, etc. Highly recommended. And within economics, sort of the paper that I'm drawing most inspiration from is a paper by Josh, Mahmoud, and Sarangi, I think, which I think this paper was presented in GamesNet, if I'm not mistaken, right? So the type of coupling between networks that they do there, I'm also gonna do here. The type of model I'm gonna write down is very much related to Acemoglu's, Daglar, and Salehi's paper in 2015, in the sense of, you know, this reduced form framework modeling. And finally, with regard to systemic importance, well, I put the Ballester-Calvo-Zinu paper, the famous paper here, although my definition of key is not exactly the same as theirs, right? So their classification of key agents was not the agent who transmits a shock, but, you know, I take an agent out of the system, and, you know, what's the largest change in aggregate actions, if I'm not mistaken, is what they do. But regardless, sort of the principle remains the same, right? It's a centrality argument there, and there it was the intercentrality that mattered, but intuitively, sort of, when theoretically speaking, it's a similar type of argument, right? I also need to bring out that multiplex in economics, there has been sort of a recent sort of boom in empirical multiplex finance. And there, you know, people have been starting to realize is that you know, financial systems are of multiplex nature, right? And we need sort of paint a complete picture of the financial system and systemic risk only if I can take into account the full multiplex. And finally, with regard to volatility, there is a long literature in macro as to, you know, the effect of the disparity between micro idiosyncratic and aggregate shocks. And sort of this literature culminated with you know, a Semoglu's Douglas Carvalho paper, a famous paper in Econometrica, where they show that, you know, network effects matter, and indeed aggregate volatility can be very large when you have very asymmetric connectivity structures. Any questions up until this point before I jump into the model? I know I've said a couple of things, so. No, all right. So let me give sort of a bird's eye view of the model that I'm going to write down. And again, this is inspired by that introductory slide and the sort of general formulation of economic network models, right? So essentially what I'm going to have is n agents that are sort of embedded in M layers, right? M networks. And I'm going to use networks and layers here interdependent. In each layer, how are these agents classified? Essentially, they're taking they have a vector of actions, right? A vector of states. So in each network, agent I, in network K, for example, they exert a particular action, and this action will be taken to be a response to everybody else's activity, right? So I'm going to write down a general function f that governs the level of this action based on what everybody else is doing, and down some properties and go from there. As I briefly mentioned before, so these actions bilaterally, so actions between, say, network 1 and network 2, will be taken to be either strategic complements, substitutes, or independent. So this is where the multiplex is going to come in. And then sort of the last two ingredients, we will have some aggregation function, some G that takes all these actions, right, and maps it to some aggregate statistic. And we're going to come in and sort of hit a particular agent in a particular layer and see the response. Essentially, what we're going to do is a perturbation exercise here. That's what the paper does. And yes, I'm going to take a Taylor expansion and see the response. So that's what I'm going to do. So let me begin with actions. So this is how the activity level is taken here. So essentially what I'm going to say, I'm looking at here agent I, a particular agent I, in a network, in a particular network K, right? And this action is taken here to be a response, Fk, some function Fk, which maps the following. It takes the activity levels of the same agent in all other layers, right? So it has a direct dependence on what it is you're doing. Excuse me. So it has a direct dependence on the activity levels of what it is you're doing in these other layers, right? And it also depends on the interaction structure in the particular layer, right? So this sum of a Gij here is sort of the network interaction, right? This is where the networks come into play. And epsilon ik here is just an agent layer specific shock that we're gonna activate later on. Now, a brief remark on the networks here, these Gijks. So the networks that I'm taking here are weighted and directed, and the interpretation here, so each of these G's is between 0 and 1. And the interpretation here and the way to sort of read the indices, and the indices are a nightmare in this paper, so please, The trick that you do to sort of keep track of everything is that this is to be interpreted as from right to left. So you read the indexes from right to left. This says in network K, right? In network K, the extent to which agent J influences I, right? So this is the interpretation of this G. So the larger this is, sort of the more influence J has over I, right? That's the story. GIIK equals 1, then yes, the agent I has no links essentially. And we're going to take all these, put them in a matrix, and we call this the weighted adjacency matrix of agent K, right? And one assumption that I will make here, which is important to the analysis, is that I'm taking these matrices, these adjacency matrices, to be row stochastic. So the row sums will be equal to 1. And the interpretation here is that you're saying that the total impact any agent can receive, the total influence that others can have on him or her is fixed, right? So again, rows here have to do with influence that is exerted on me, and columns is influence that I exert on others, right? And it's the column sums and that are going to be important here, right? This is where the centrality is going to come in. So, okay, this is very general. So let me endow some properties. I'm going to assume that 0 here is an equilibrium. So when everybody is inactive, your activity is 0, right? That's all it's saying. And the analysis will be conducted around this equilibrium, right? I'm going to start in the inactive state, introduce a shock, and see how the system responds, right? That's what we're going to do here. I'm going to assume local complementarity here. That is, within its network, actions are strategic complements, right? And furthermore, at 0, again, since we're doing the analysis at 0, I'm going to assume that when you take sort of the first derivative when you take the derivative with regard to activity within a particular layer, this gives you back some lambda. And for those of you who know the linear quadratic game, you know what this lambda stands for, right? It's the same lambda here. I could take this lambda to be layer specific, say put it equal to lambda k, but this doesn't change sort of the intuition of the results or anything. It just makes things more messy, I guess. And tracking centralities with different lambdas is horrible. Now, the most important assumption, again, as I talked about before, is this property, the strategic coupling property that I'm endowing. And essentially what I'm saying is that if you sort of take the derivative of this activity level with respect to your activity in some other layer, right, this will dictate the strategic interactions, right? So we're saying that if this is positive, if the derivative is positive everywhere, then these are complements, right? If it's negative, this is a substitute. And what I'm going to do is that around this inactive state of 0, I'm going to just set this guy is equal to some gamma, right? Some gamma that is network specific. So this says that your activity in network K is complements to that of I if gamma Km is positive, right? And this gives a very nice sort of geometric interpretation to the multiplex. Please.
Hector,
yes.
Hector, very quickly. So if I assume complementarity, then I assume complementarity for all agents. If I assume substitutability, I assume substitutability for all agents, right? I cannot simultaneously have. Okay.
Absolutely. Hypothetically, you could, right? But it makes this a complete nightmare. It makes it a complete nightmare.
Yeah. Because you have to keep track of, opposing forces.
Absolutely. And honestly, I think that a more mature version of this model will take this into account, right? But here we're just sort of trying and understand how the system works. So I'm gonna make my life easier. Right?
Can I ask you a question too, Hector?
Please.
I can see that if you have a linear quadratic model, the first assumption, the one that fk01 is equal to lambda, is not going to be, it's going to be true no matter where you are. But how could you build a model where it makes sense that the complementarity that you have across layers at 0 will remain the same everywhere? I don't know if I'm making myself.
Right. No, it's a very good point. So the idea that I had behind this, right, is that because I want to do sort of a perturbation analysis, I need to evaluate these derivatives at a particular level, right? And essentially, what I'm saying is that the equilibrium of interest here, right, is 0. I could take it to be some other equilibrium, say, alpha or x or y or whatever, right? So all it is I'm doing, right, is I'm saying that, look, this is some number, right, that is going to be of interest. Again, I'm not saying that this, in any model you write down, this lambda is invariant to equilibrium, right?
Right. But it would be if you had the model in which you multiply just xik by xim,
yes.
right? So that's what we should think of in the background.
Yes. So indeed, I'm going to do a linear analysis here, right? So everything will be similar and isomorphic to the linear model. But in a perturbational sense, you need to set these values to something, right? Otherwise you cannot say much. But it's an excellent point. Thank you for raising it.
I also have a question about your the best response function.
Yes.
So you're saying that my best response player I in a layer K somehow depends on what's going on with my neighbors, right? My friends on a layer. So that's the first term. But on the other layer, it seems only depends my own action, but does not really depend on my neighbors or the aggregation of my neighbors' action in the other layers. For K is different, for J different from K. But in principle, you could do that, right? You could just incorporate that.
Absolutely. In principle, you could. So essentially, what I'm saying here that it's the direct dependence is as such, right? Indirectly, right, as we will see, it will also depend on your friends and neighbors on the other layers, right? Absolutely. I could, do a similar argument here and say that, it's not xi1, but it's, as you're saying, the sum over the xi's times gi's over that layer, right? I haven't explored this directly, but the point of this best response is directly motivated by the definition of a multiplex, right? So this is the idea here. What would happen if you introduce these direct sums into this framework? I cannot say for sure, but I probably will speculate that type of system will start to resemble a single layer, monolayer type of framework, particularly in the linear approximation.
Are you going to have a micro foundation with some kind of utility function?
So yes, in the
generate
paper,
this kind of FK endogenously.
Yeah, in the paper I do have two of them. I don't think we will have time here for today, but as was mentioned before, a linear quadratic setup does give you these dependencies. And I also explore very simple general equilibrium, firm, multi-sector, multi-firm consumers type of framework that also gives you that preserves these functional relationships isomorphically computed. So you can take a look there if you're interested. Quickly, what I was saying is that this strategic interactions assumptions produces sort of this alternative representation of the multiplex, right? Essentially, what we did is we took this manifold layer embedding version of a multiplex, and we constructed a strategic representation of it, right? So you can think of it now as a supergraph where each node is the actual network, right? And links between these super nodes, which are now the networks, is the strategic interactions parameters. Let me go back to actions. And again, and finally, another sort of assumption that needs to be made here is that this map is non-expansive. This is sort of the minimal thing I need to sort of write down these equations in the first place, right? Because let me go to the next slide quickly, but keep this in mind. Essentially what I'm going to do is I'm going to define a trivial equilibrium here. I'm going to define an equilibrium trivially and just say, the equilibrium is where the system of equations is satisfied, right? Again, best responses, you can think of this as best responses, and then the solution occurs where the system is satisfied. And then in this general framework, yes, the only thing that we can say is that, this system exists if these maps are non-expansive. So now let me do some comparative statics, and this is where these margins that I talked about previously are going to arise. So essentially, what I'm going to do, as I said, is start at this inactive state at 0, right, and look how actions now will change if there is some shock epsilon I k to agent I in layer k, right? And that will tell me essentially how this shock will transmit not only within, but as well as across, right? Oh, and quick reminders before I do this. These are two objects here that I'm going to need to interpret the result. This is, the influence matrix of a particular network is the I minus lambda GK inverse. And what does this tell you? Well, the elements of this matrix here tell you, the total influence that J exerts over I, right? The G's were direct, and the M's here capture total influence, right? So it's your neighbors, your second order neighbors, third order neighbors, etc. Right? And Bonacic here, Katz-Bonacic, essentially I'm taking the column sums, right? These are weighted networks, so it's not, the sum is not symmetric anymore. All right, cascades, so comparative statics essentially. So I'm going to start in layer K, right? I'm going to start at 0, and I will go to agent R and distress him, right? I'm going to activate the shock epsilon RK. And when I do this, you take the derivatives and you solve, you get the following expression. You get that the adjustment, right? The adjustment that any agent in the distress layer, so this is agent I in the layer in which the shock is realized, is a response, right, to the total influence the distress agent exerts on him, right? So this is these M's that I defined before. Let me hold on to this. I'm going to explain what this is in a bit. This nonlinear order in gamma. But how you get this? Well, this is the standard, the standard argument. You have some network, the shock comes in, agent 2 is distressed, and then sort of the shock transmits from him to his neighbors, and then from his neighbors to their neighbors, right? So, like so. And this is where this M comes in. Now, the second thing that happens, besides the adjustment within the particular network, is that the strategic interactions here induce action adjustments not only where the shock is realized, but also in other layers, right? And what is the story here? The story is as follows. You have now two networks, right? You have some network K and some network L. So essentially what happens is that when you distress now the same agent that we did before, agent 2, right? So you will have a response in layer K, but you also have a response in layer L because of the strategic interaction, right? So what happens here, right, is as follows. Agent 2 gets activated in K, the distressed agent, and the distressed layer, but also responds in network L, right? This response in network L now, right, will act as a shock on network L, right? And you can now continue this process. So this is what happens when the shock is realized. Then what happens is, agent 2 will transmit the shock in the same network. And then from here, agent 2, again, will transmit it in network L. So essentially, you can interpret here the red dots, the red activations have to do when the shock transmit within the layer, and the green ones are activations because you get activated in the other network, right? Does that make sense? I think. And you get this cascade now, right? You get these constant activations across networks as well as within. And one thing to note is that I can play this game infinitely, right? I can think of networks being activated within networks being activated on some other layer, right? But then these activations will need to cause a similar activation back on some other layer, right? So this is the gammas here, the order, this is what you're seeing here. So, you know, a shock occurs in layer 1, it transmits to layer 2, and then from layer 2, it needs to transmit in layer 3. To keep this tractable, right? And so we can interpret the results here. I'm going to take these gammas here to be small. So essentially, I'm just going to look at linear order in gamma, right? And the interpretation here is that I'm only allowing a shock to cascade across networks once, right? In the paper, I do discuss how to account for higher order interactions, but as you will see, it's completely messy and it's very hard to interpret. It's not that hard to interpret, but it's hard to sort of, you know, say anything with regard to aggregate outcomes. So I'm just going to tie my hands around my back and say, look, these are small. But again, if we can say, at the end of the day, if we can say that, you know, multiplex interactions matter even under weak interactions across networks, then they are important, right? So this is the interpretation I give here. And this just says what I said before, right? This is the mechanism here. Now, are there any questions on this? Because this is sort of the heart of the paper, right? I'm just going to use this now I'm going to map this to systemic importance and fluctuation. No, okay. So quickly, the aggregate state here works in a similar way. I'm just having some aggregator of aggregate activities. So you have some function g, which is a function of functions h. So h essentially will aggregate the economic activity of agent I, and then g aggregates all aggregate activities. You can do it another way because, of course, this is a linear approximation. We could have an aggregator of aggregate layer activities, right? So the results will be the same in the linear approximation. Quickly, I'm going to assume that at 0, this aggregate state is 0, and two more assumptions that I make here is a diminishing agent and layer important assumption. Essentially, what I'm going to say is that these things, these G's and these H's, are inversely proportional to the number of agents and the number of layers. So think of Cobb-Douglas production with consumers. At equilibrium, you have that the value function is proportional to 1 over n, right? So this is a similar argument here. And essentially, yes. So the more layers or agents are present, the less dependent the system becomes on any particular one, right? This is the interpretation. And this, of course, will have importance in the fluctuation and distributional argument that we're going to make later on. All right, and we take the same. Finally, we take a Taylor, right? We look at a linear approximation of this function A, which looks something like this. It's an expression with 4 sums, so it's a bit hard to keep track of. But all this is saying, right? All this is saying is that, look, I'm just summing here over all the shocks that can be realized. There are n agents in m layers, so I have this is what the sum is doing. And these weights here on the shocks are essentially these margins that I talked about, right? So BRK is simply the Bonacic centrality of agent R in layer K, right? So this says that if there is a shock in agent R in layer K, right, the aggregate effect I get due to inter-network cascades is simply the centrality, right? And the aggregate effect I get due to cascades across networks is given by this weighted sum of centralities now, right? And again, this simply comes by summing over, because it's the linear scenario, this comes by summing these inter-network action adjustments that we saw before, right? And this simply now gives us the tools required to answer the two original questions, right? Again, in the single layer, if we go now and ask, all right, I have this equation now, right? Then I can ask, all right, if I normalize all these shocks, right? If they, I don't know, set them equal to 1, for example, which one will give me the largest response, right? Which one will give me the largest aggregate response of the system? Which is this equation here. Again, as discussed previously, if I set now all these gammas to be 0, right? If multiplex interactions do not matter, I come back to the single layer case, right? I say the most central agent is clearly the most important in the system, right? But now if we activate these gammas, this might no longer be the case, right? This term, this second term here, this inter-network margin, can be large enough to induce a reordering of systemic importance, right? Now, since I'm running out of time, I want to do this as fast as possible. This is sort of the necessary conditions that you require to sort of classify systemic importance in words. The actual proposition is a bit messy to cover in a seminar. But intuitively, like, it is what you think you're going to get, right? So say you have a collection of networks, right? You have, say, 3 networks. And all of them are complements, right? The activity levels that are undertaken between them are complements, right? Then you need to, for some agent to be systemically important, you need him to be very central in all the networks, right? And why is this? The reason is, if you disturb one of them, right, then when the shock transmits, it has the same response, right? So if there is a positive shock to that agent, there is a positive response due to the strategic interaction in these other layers, right? And since these responses become now shocks within them, if it turns out to be central in those as well, right, then you get a large inter-network margin. But now what we can do is to say that, look, what if there are substitutes, right? If there are substitutes, if I disturb one of them, then you get inverted responses in other layers, right? So this can reduce the relative effect of the shock, the relative effect that the shock can have on the aggregate state. And I have an example here, and I think I briefly mentioned this in the beginning. We have 2 networks, K and L, right? And they are coupled together by some gamma, some strategic interaction. And we can actually go ahead and compute centralities here for each of these layers. And we will indeed find that agent 1 is the most central, Bonacic-wise, in both layers, right? But okay, if I couple them positive with a positive interaction, then you get that indeed 1 will also remain most important in the aggregate system, right? But you can show that in this scenario there exists a gamma, right, such that 1 is no longer the most important in the system, right? And I think this is quite a surprising result to me, to at least the very least of how we think about networks, right? So if you're interested in a particular system that happens to be, you have data, say, on a particular system that has a network interaction within it, right? Then you naturally would assume that, if I have a systemic importance sort of policy question in my mind, then I need to identify centralities here, right? Because he would be systemically most important. But it turns out that, if the system is not single dimensional but is multidimensional, there exist these interactions between them, then that's not the end of the story, right? There are more things here that need to be taken into account. Now, I only have 5 minutes left almost, so I want to quickly run through.
You can take 7-8 minutes easily because we start 3 minutes late. You can take 7-8 minutes. Don't worry.
Okay. Okay. Then let me pause and ask if there are any questions on this. I hope I was clear. No questions. Okay. Great. So and now sort of the last thing that I want to do is to now try and see what can be said with regard to fluctuation tendency here, right? So we had this approximation of the macro state, of the aggregate state, and we have said, I remind you that these shocks are their mean is equal to 0. The fact that we say these are also IID, and the fact that they're IID in the macro literature, they call this, we don't have aggregate shocks in the economy, right? And to sort of say something about the distributional properties of this macro state, what I'm going to do is simply look at the variance, right, at the standard deviation of this object. These shocks here have some, they have mean 0 and some layer specific variance. And I'm just going to look at the second moment here, right? I'm just going to look at how large the tail should be. Simply think of these shocks as being, in this case, a simpler case, think of them as being normal with some 0 sigma squared distribution, and you're simply looking at the tails, right? That's what we're going to do. And maybe most of you have seen this before. This is, Somoglu called this aggregate volatility, so I'm going to do the same. And to give you a bit of more sort of background of what's going on here, is that you can take the standard deviation of this and write it in this bit of ugly looking expression here. So what I'm going to do is to break this up and sort of see its elements and see what it is that matters here, right? To classify this volatility. And indeed, we can take this expression, and under the square root here, each term behaves as follows. This is what matters here. So we see two things. So first, the first thing that I want to do is recall that this aggregate state here, right, this aggregate state, I assumed that it was inversely proportional to the number of agents that are active, right? So I said that this A is inversely proportional to 1 over n to the beta for some decay beta, which is given by this CG here, this constant CG. Now, if we look at this norm, right, this is just a 2 norm. If there are no networks at all in this economy, right, this object here, variance of A, the standard deviation of the macro state, as I increase the number of agents in the system, right, sort of dies out at this rate, at n to the 1/2 minus beta. And what is this? This is, the standard diversification argument in the standard Lucas diversification argument in any economy, right? If you have, say, a collection of agents that populate a system, it's facing idiosyncratic shocks, right? Then the relative effect that each of these shocks can have on an aggregate state is minuscule as the number of agents increases here, right? If you add the network, right, within this across these agents, then you have this additional term here, right? This is the variance of the Bonacci centrality. And the story here is, and suppose these gammas are 0, suppose all these terms is 0. If I have a network, right, then then asymmetry in centrality is what governs fluctuation tendency. And this is the argument I made in the beginning, right? And this is where it comes from formally, right? You have this variance here. And the story is, if this variance, if this network exhibits asymmetric connectivity in that as I populate the system with more and more agents, this variance grows at a rate which is higher than n, then you have higher than natural fluctuation tendency, right, without the network. And the whole story here is that if I now, say that these gammas are non-zero, I get this additional term that might also affect the aggregate volatility in the system. Now, the thing to note is that this analysis is done in the limit, right? I'm looking at the large agent limit here. And the reason is obviously that it's very hard to classify these objects in closed form, right? It's almost nearly impossible to compute the influence matrix of any graph, of any arbitrary graph in closed form. So essentially, to get sort of a feel of how this behaves, I'm going to look at, as this increases, what happens to the asymptotic, what is the asymptotic behavior of this object, right? That's the argument. And as you might expect, again, it has to do with the gammas, right? It has to do with interactions across the layer. And the result simply states, right, that the aggregate volatility, so aggregate fluctuation tendency, the rate at which it decays as I increase the number of agents, is decreasing in the number of complementary network pairs which exhibit positively covariant Kac-Bonnet centrality vectors, right? And the idea here is again the same as in the systemic importance argument. The idea is simple, right? So we take some network K, right, that exhibits large variation in centrality, right? Large asymmetry in centrality. What does that imply? This implies that you have a small number of agents that are most central in that layer, right? If I take some other layer, GL, L, such that the covariance between the centralities of K and L are positive, then this implies that the same fraction of agents is also more central in that layer, right? This other layer. If these layers are coupled by strategic complementarity in the scenario, right? Then essentially what happens is that large shocks to in any of these two networks, right, will cause a large inter-network margin, right? A large response according to the inter-network margin. And simply this result states, right, that this margin, whenever this is the case, will dominate the natural decay and might result in larger volatility, right? That is simply the argument here.
So Hector, can I stop you for a minute? So
Please.
If I were to look at the last part of the paper by Acemoglu et al., which is the comparison across networks to see which networks will create the more volatility, do you have something to say here about how should I put layers of networks in a way to minimize volatility?
Right. So if you want to minimize volatility, right? So what you would do is, suppose in one network you have a star, right? So you have high volatility in one of them, right? High asymmetry in one of them. So in the other network, what you would want to do, if they're coupled with a positive, if they're coupled strategically complementary, is the coupling, then essentially you want large centrality agents here to be very small here, right? That's the idea.
If you have more than two layers, it becomes more complicated, right?
Well, yeah, it becomes much more complicated, absolutely. But let me also just say that because I didn't talk too much about substitutability in this argument, is that when you have substitutability, you don't really care how you couple them, right? Because if I have layers being substitutes, what I'm doing is you are diversifying the system in all accounts, right? You are increasing the dimensionality of layers. This is diversification, but you're also diversifying actions as well, right? So some positive shock here produces some negative response over here, right? So this diversifies the system in all accounts. So the bottom line here, once again, right, is that complementarity can amplify can amplify these results, right? So say you end up being more volatile and end up being sort of above Acemoglu with regard to volatility, as you mentioned. But then substitutability, I can also get a more diversified system, right? And maybe in the financial context, right? Maybe this we can think of this in the financial context, right? Where banks take positions to diversify some portfolio, and therefore activity levels across networks could be substitutes, right? So I'm thinking this is the type of system I'm thinking about. Now, I think I've said a lot, and I'm sorry if I made myself dizzy a bit, but let me skip this and simply conclude. So what we have at the end of the day, we simply have that a multiplex view introduces new channels through which shocks can transmit. Single layer centrality not enough for systemic importance, as long as you have these interdependencies across the system, across the layers. It could be more volatile, or it could be less volatile, depending on the coupling structure. And as I briefly mentioned before, I think that this has sort of empirical consequences whenever the person conducting the empirical exercise is interested in sort of network effects, right? If the system of interest happens to be exhibits network connectivity between the agents that are populated, and sort of intuitively as well, more often than not, agents interact across multiple dimensions. And if that's the case, these things need to be taken into account. Analysis for possible applications, macro trade finance. I talk about applications more in the paper. I'm sorry I didn't have the time today. But if you're interested, you can definitely take a look. And in the question that was asked previously, this model can indeed be mapped isomorphically to particular systems. The linear quadratic, it maps perfectly, I think. So I think that's all I wanted to say. So thank you, and thank you for your questions as well. Yeah.
So, Hector, can I ask you a
yeah,
question?
please go ahead.
Yeah. So I'm a macroeconomist. I know very little about networks, but just looking at the model, so here a person's action is spread over all the layers, right? One person is active in all the layers in your model. So suppose I think about an alternative scenario where each layer is populated by, a set of people, right? So, but they're connected, so my intuition is that, of course, the model would be simpler, right? But my question, how much do you lose out by taking, this approach in terms of the results?
This is an excellent point. I have an extended footnote in the paper on this. Well, what is it we did here, right? We said you don't really need to say that these agents are the same, right? So think of simple case, right? Two components of the system, right? You have one layer here that is populated by some agents that take some action X, right? And you have another set of agents here that take some action Y, right? There is nothing constraining me here to say that action X1 and action Y1 are taken by the same agent, right?
Right.
If I write down this type of model, right, this type of interdependence the way I did, all I would need to do to maintain these results is to say that there is a unique correspondence across the layers, right?
That's right.
You can make it now more complicated, right? And to say, look, there is not only one correspondence between them, but there are multiple correspondences now, right?
Mm-hmm.
In this scenario, what you get is what we call a multi-layered network, right? This is called a multiplex. These are called multi-layered or multi-graphs. But intuitively, if you think about it, right? If I have these two layers, and even if I have different agents across them, suppose I start with a unique correspondences and I know how to deal with that. Now, if I have multiple correspondences, essentially these multiple correspondences are embedded in the single correspondent case, right?
Sure.
So if I know how to deal with this, I know how to deal with the more general case. If it's tractable, that's another story. But it feels like these propagation sort of arguments here and how shocks can transmit, for example, right? It has a similar feel, right? That's what I want to say, yeah. But it's a very excellent point.
Yeah, no, what I'm trying to understand is that the qualitative results that you have in your, do you lose out anything specific by, if you take the alternative approach? So
I don't think you do, right? If you think that these are different agents here, right?
yeah.
It doesn't really matter what you call them, right? I think.
But the model could be simpler.
Yes, I think maybe.
You know, but you can preserve the same set of results. Is that true? Oh.
I mean, the functions, I think, if I write the same model, I could write the same model with different agents. If you do it, how to make it simpler? That I need to think about. I mean, how you would do this?
Just, you know, just.
No. It's actually an intriguing question, right? And you made me think. If I come up with an answer, I will definitely maybe send you an email. We can discuss more. But the thing that I want to say is that sort of the particular model that I wrote down here. Forget about the possible simpler version of it. But the particular model right here could be also interpreted in this context, right? That these agents and these agents are intrinsically different, right?
Sure.
But there is some unique sort of strategic interactions across pairs of agents in this system, right? You can also think about that.
Sure.
Thank you, Hector. Any more questions? Diganta, Rajnish, can you?
Yeah, so I was just curious about this work that you are showing, Hector, about the comparative statics. Have you done any simulations or numerical work?
I did so. These examples that I did here, these are all numerically driven, right? You know, I state them here very analytically, but you know, all these, you know, what level of gamma here do I need to actually get this result that I talked about, for example, right? I think that this is a two-layered case. I think this gamma here is about minus 0.2, right? So this is a majority of parameterization here that these results hold. Definitely, I did some numerical exercises to motivate the proving of these results, right? But simulation-wise, I think the good thing here is that you can actually simulate this, right? And sort of play around with various shocks and various parameters, etc. What I would do if I were to sort of be serious about simulating this would not only be sort of, you know, playing around with this linear approximation, but also now take more and more approximations into account, right? Because this is something that cannot be done analytically. Our hands are tied here.
No, but when you say more than linear, then your expressions will go beyond matrix algebra, right? So how would you handle them numerically?
Oh, essentially what you do is you take more terms in the Taylor expansion, right? And a computer can do this. It's all very hard.
I understand, but as soon as you get into the next term, it will go beyond quadratic forms.
Excuse me, you got stuck for a moment, and I missed the final point.
Yeah, no, okay. So I was just wondering that if you get into the next higher order term, he will go beyond the quadratic form, and then it is going to be a computational nightmare. So.
Oh, absolutely computational nightmare. Absolutely computational nightmare. But again, with regard, for example, let me talk about non-linear interactions with regard to, say, the aggregate volatility. So there, right, remember, we have this gamma squared, gamma to the cubed, gamma to the fourth, etc., right? Indeed, these terms, right, these terms are given by in also what they multiply are infinite series of influence matrix compositions, right? At some point, computationally speaking, you need to stop the approximation somewhere, right? You need to say, look, I'm going to consider powers of gamma up until, say, 5, but you also need computationally to say, I need to also stop the lambda somewhere. It's not just gamma, computationally. I have an appendix in the paper that I do talk about how you sort of interpret, and I do show you sort of how this looks like. But computationally, when you stop this, what's sort of the best approximation that you can do, right? By and keeping sort of generality here, that's a question that I unfortunately do not have the answer to. But it's a good point.
I am not surprised. Yeah, it's a very difficult path to take. Okay, thank you.
Thank you. So, Diganta, can you take care of?
Yeah, okay. So, Hector, it has been a very nice presentation. I think all of us have enjoyed it a lot, and there are many questions, but of course we have to, continue this offline. Best of luck for your
thank you, and thank you,
job market.
Thank you so much. Thank you so much for having me.
Career.
It's truly an honor, and thank you so much for your questions, and I look forward to the next seminar.
Yeah, enjoyed a lot, Victor. Thank you.
Yeah, do join us every time, and thanks to all the participants. Thank you. Good night, or good afternoon, or good morning, or good day, depending on where you are. Bye-bye.
Bye. Thank you.
Thank you all. We'll meet in the next.
So do we have a date and topic yet? Or?
I think some speaker is fixed. I don't think we have the topic, but we'll send in the due time.
So it's typically every alternate week. So